Hi, it's Double O Pi, your undercover chemist here. Today we're going to be talking about kinetics, specifically how to determine reaction orders and rate laws from experimental data. So let's talk about what a rate law actually is. Essentially, it's an equation that equates the rate of a reaction to a formula that includes the concentrations of all your reactants. So if you have a reaction with two reactants, A and B, it doesn't really matter what your products are, then your reaction rate is going to be written like this. Your rate, whatever that is going to be some constant, K, times the concentration of A to some power M, times the concentration of B to some power N. So you can see that the powers here are different or could be different for different reactants. Now, how do you know what those exponents are? The answer is you can only find out what they are experimentally. You can't tell them by looking at a balanced equation. Let's talk a little bit more about reaction orders, which basically have to do with these exponents next to the concentrations. So each rate law includes the concentration of a reactant raised to a power. You can have first order reaction, where basically you're raising the concentration to the first power, A to the 1. You can have a second order reaction, where you have the concentration squared, so second power. You can also have something that people rarely think about, the concentration raised to the 0th power, which we call a 0th order reaction. The reason this reaction order is important is that it affects how reaction rates change with concentration. Let's look at what happens if we keep the concentration of B constant but change the concentration of A. And we're going to look at that for the different reaction orders. Okay, so first order, here's our rate law for an equation which is first order in reactant A. We don't care at this point what the order of reactant B is because we're keeping our concentration there constant. So let's see what happens if we change A. If the concentration of A is some number x, plug that into the equation. Your rate is going to be your rate constant K times x to the first power times the concentration of B to whatever power it's raised to. So Kx, concentration of B to the n. What happens if you double the concentration? If you double the concentration of A, now you have A equals 2x, and your rate is going to be 2x to the first power times K times concentration of B to the n. And you can rearrange those and see that that's 2 times the quantity Kx B to the n. In other words, it's 2 times what it was when we had concentration of A equals x. If you have 3 times the concentration of A, the rate is going to be K times the concentration of A to the first power, so 3x to the first power, times the concentration of B to the nth power. And we're going to rearrange that and get 3 times the quantity Kx B to the n. In other words, we tripled the concentration, and that tripled the rate. So overall, our rule for first order rate laws is that if you increase the concentration by any factor, let's call it n, the rate is going to increase by the same factor, n. Okay? So here, again, we increase it by a factor of 2, the rate increased by a factor of 2. We increase by a factor of 3, rate increased by a factor of 3. Now let's go back, let's look at the same rate law, except with one difference. We're going to make it second order in A. So once again, A is changing concentration, B concentration is constant. The only difference here is now we have the concentration raised to the second power, the concentration squared. So let's start out again with the concentration of A being some random number x. Plug that into the rate law. You get your rate is K times x squared times concentration of B to the nth power. So we're going to rewrite that as Kx squared B to the n. And then let's look again at what happens when you double the concentration of A. So now concentration of A is going to be 2x, and now we have to square that quantity 2x. That's going to give us 4x squared. 2x quantity squared is 4x squared. And let's rearrange that again. What we get is 4 times the quantity kx squared b to the n. What happens if we triple A? Now the concentration of A is 3x, and when the concentration of A is 3x, then our rate is going to be k times the quantity 3x squared b to the n. So quantity 3x squared is 9x squared, and so our rate is going to be 9 times the quantity kx squared b to the n. So let's try and sum this up in a simple rule. For second order equations, if you increase the concentration by a factor of n, whatever that factor may be, you're going to increase the rate by a factor of n squared. So let's go back and look at that. Here we have double the original amount, 2 times the original amount, and the rate is now 4 times, so that's 2 squared, 4. Here it's 3 times the original amount, and it's 3 squared, 9. So once again, you increase the concentration by a factor of n, and that increases the rate by a factor of n squared. Now let's look at zeroth order. Zeroth order is where your concentration is raised to the 0th power. So once again, we're going to try changing the concentration of A while keeping the concentration of B constant. When concentration of A is x, we plug that in, k times x to the 0th power times b to the n again. X to the 0th power, well, anything to the 0th power is 1. So our rate is going to be k times concentration of b to the n. That's it. What happens if you double the concentration of A? Well, if you double the concentration of A is 2x. You plug that into the rate law, and you could see that we have 2x to the 0th power. Well, what's 2x to the 0th power? Same as x to the 0th power. It's 1. So our rate is, once again, it's k b to the n. What happens if you triple concentration of A? The rate is going to be k times 3x to the 0th power. What's 3x to the 0th power? 1. So once again, our rate is k times concentration of b to the n. So what is our law for 0th order reactions? Basically, it doesn't matter how you change the concentration, the rate does not change. The rate of the overall reaction does not change with the concentration of a reactant that is 0th order. Let's put that into practice. I'm going to show you how you can use experimental data to determine the order of a rate law. Remember that I said earlier that those coefficients in the rate law can only be determined experimentally. So what we're going to do is we're going to look at experimental data, and we're going to use that data to determine the rate law. And so the rate law is not this generic law that you see up here, but we actually need to fill in these numbers that we don't know, this constant k, which is different from reaction to reaction, and these two exponents, m and n. So how do we do this? First of all, we're going to do the rate orders one at a time. So we start with the first one, which in this case is concentration of A, but you start with your first reagent. So in order to make this work, you're going to need experimental data with 3 different sets of concentrations. You'll see that when we look at our first problem. What you're going to do is you're going to start off by determining the order of the first reactant first, and you're going to find 2 data sets where the concentration of that reagent you're looking at changes, but the other concentrations remain constant. And then we're going to look at the first order, second order, or 0th order rules to determine which rate order is appropriate for that particular reagent you're looking at. And so you might start off finding the order of reagent A. You can see step 2, it says repeat step 1. In the rate law we have up here, the next reagent is B, so we'd have to calculate that for B, go through the same steps. You could actually have several reactants in there, so you could also do C if there's a C in the reactants or D, whatever, however many you have. Repeat that as many times as you need to. Then finally, once you have determined all the rate orders, what you're going to do is you're going to take experimental data, plug it into the rate law, and solve for your rate constant K. Okay, let's look at our first problem. Here we're looking at the reaction where you take 2 molecules of nitrogen oxide, 1 molecule of oxygen, and that produces 2 molecules of NO2. So here you can see that we have 4 different experiments with different concentrations. We're changing various concentrations of product, and for each set of concentrations we have an initial rate of reaction that we're going to use. Okay, so let's start with step 1, which is to find 2 data sets where the concentration of the first reagent changes but the other concentrations remain constant. So I'm going to start off doing NO, and it really doesn't matter which order you do the reagents in. Okay, I'm going to start off by doing NO, though, because it's first in the table. And I'm going to look for something where the concentrations change, but the other concentrations remain constant. So if you look at these first 2 rows here that I've highlighted in orange, you can see that the concentration of NO changes from 0.04 to 0.08, but the concentration of O2 does not change. You've got 0.02 in both cases. Okay, so the first thing we do is we look at how much the concentration changes. The second set of data has a concentration of 0.08. The first set of data has a concentration of 0.04, so it's increased by a factor of 2. How does that affect the rate? Well, in the second set we had 0.192, and the first set we had 0.048. So you divide those, you see the rate increases by a factor of 4. What does this tell us about the rate order of nitrogen oxide? Well, our concentration is increased by a factor of 2. If it were first order, that means the rate would increase by a factor of 2. It didn't do that. Second order says increase concentration by a factor of 2. That's our N here. If it's second order, the rate would increase by a factor of 2 squared, which is 4. So that is what we see here. That's a second order reaction in NO. So let's remember, I'm putting it down at the bottom of the screen, we have second order reaction in NO. Now we're going to go through, we're going to look at our other reagent because you have to determine the rate order for each reagent separately. Once again, we're looking for something where the concentration is changing for the reagent that we're interested in, but it stays the same for the one we're not interested in. So I picked 2 here where that works. We're doing dataset 1 and dataset 3. So you can see that the concentration of NO remains the same at 0.04, but our concentration of oxygen is increasing from 0.02 to 0.04. So let's look at how those change. First of all, how does the concentration change? Well, it's changing from 0.02 to 0.04. In other words, it's increasing by a factor of 2. Remember, you can always find that increase factor by dividing the bigger one by the smaller one. What happens when we increase the concentration by the factor of 2? What happens to the rate? How does the rate increase? Well, it increases from 0.048 to 0.096. That's a factor of 2. So now let's check against our rules. First order rules is if you increase by a factor of 2, the rate would increase by a factor of 2. And that is, in fact, what happened. So this reaction is first order in oxygen. Now we get to do step 3. We have our orders for both of our reactants. Let's take our experimental data and the rate order exponents we just got, plug them into the rate law, and solve for K. So here's a generic rate law for this reaction. Rate is K times the concentration of NO to some power times the concentration of oxygen to some power. Now we know that we've determined this is second order in NO and first order in O2. So let's actually put those exponents in there. And now we're going to take actual experimental data from the table and plug it into this rate law with the exponents. I'm going to use row 4. It doesn't really matter which of the rows you use. You should get the same value of K for each. So what we're going to do is we're going to take those numbers and plug those into the rate law. So you can see I took this 0.384, put it in for the rate. I substituted 0.08 in for the concentration of NO, and I substituted 0.04 in for the concentration of O2. Now you can solve for K. And what you get is that K equals 296. So now we could take that and we can write a final rate law for this reaction, which is that the rate is equal to 296 times the concentration of NO squared times the concentration of oxygen to the first power. Let's get a little more practice with another problem. So here's a rate law for a different reaction that involves NO2 combining with carbon monoxide to make nitrogen oxide and carbon dioxide. So let's go through our steps again. First step, remember, is to pick one of the reagents and calculate the rate order. And so we're going to do NO2. So what we need to do is we need to find things where the concentration of NO2 changes, but the concentration of the other reactant here, that's carbon monoxide, stays the same. So I'm picking those two rows. As you can see, those are the only two where carbon monoxide concentration remains the same, but the nitrogen dioxide concentration changes. So let's look at how much the concentration changes. So 0.453 and 0.151, that's an increase of a factor of 3. Now let's look at how much the rate increases when the concentration increases by a factor of 3. So we're dividing the larger rate by the smaller rate. That gives us a factor of 9. So first order rule says that if you increase the concentration by a factor of 3, in this case, the rate should increase by a factor of 3. But it doesn't. So let's go on. Second order says if you increase concentration by a factor of 3, the rate should increase by a factor of 3 squared, which is 9. That's what it is. So once again, we've got a reaction that's second order, in this case second order in NO2. So that's NO2. Let's look at carbon monoxide. What are we going to do? We're going to find two sets of data where the carbon monoxide concentration changes, but the nitrogen dioxide concentration doesn't change. And those are the first two rows. So let's look at the factor by which the carbon monoxide concentration changes. 0.814 divided by 0.407 is 2. So that's our increase factor. Now let's look at how the rate changes. The rate changes by 1. Although another way to put that is the rate does not increase at all. The rate does not change, right? You look at the initial rate up here and you see, look, they're exactly the same rate. Now, which rule fits that situation? Anytime you see the rate not changing, you realize this must be zeroth order with respect to your reagent. So this is zeroth order in carbon monoxide. Let's take that data, let's plug it into our generic rate law. So the generic rate law has a K that we don't know. It has exponents that we don't know. But now we know our exponents, right? There they are. NO2 squared times carbon monoxide to the zeroth power. What is carbon monoxide concentration to the zeroth power? It's just 1. So we can also write the rate law this way. That actually makes it easier to calculate. So let's take that. Now we're going to plug the experimental data into this rate law. And again, you can use any of the experiments on this table. I'm going to use the first row. So rate is K times NO2 concentration squared. My rate is right here, 1.4 times 10 to the minus 5th. My NO2 concentration is 0.151. We've got to square that. And we can solve for K then and get that K equals 6.14 times 10 to the minus 4th. So now we know all of our unknowns in the rate law. we can now write it with no unknowns. Our rate of reaction for this reaction is going to be 6.14 times 10 to the minus fourth NO2 concentration squared. So thank you for watching our rate law video. There will be more kinetics videos posted soon. Please be sure to check out all of our other problem solving videos. Thank you.